Hey everybody. So I'm here to talk to you today about optimism and the way we secure our rollup. So the title of the talk is The Soul of a New Machine, Next Generation Optimistic Rollup with Canon. And Canon is our fault-proof system, which is how we secure the rollup. So this talk today is all about that. So before I talk to you about how we secure rollups, I have to give you a very short introduction to what rollups are. Otherwise, this talk is going to make absolutely no sense. So this right here is Ethereum. It doesn't scale. It doesn't scale for a very good reason, actually, because it's committed to decentralization. So that anybody with a laptop and maybe SSD can, at home, validate the blockchain. You can try it at home. Maybe you've already done it. You can actually control everything that's going on in Ethereum. But because of that, nodes can't be powerful enough to scale the blockchain to accommodate thousands or even tens of thousands of transactions per second, which is what we want in the long term. So, rollups. How do rollups work? You have your Ethereum right here, and you have an Ethereum user. He has a top hat because he's rich and he can afford Ethereum. And you have the poor layer 2 users. The layer 2 user talks to a machine or a set of machines called the sequencer. And what the sequencer does is that it receives layer 2 transactions, and it executes them on its own. And then it will take these transactions, it will make blocks, it will. All right. It's better. All right. So the sequencer will receive the transactions, and it will make blocks, and it will post the blocks to Ethereum. What this means really is that it will take the transactions and put them on Ethereum, but not execute them on Ethereum. That would be very costly. You just put the data there. And also, it will post what we call an output route. An output route is something that commits to the result of executing the transactions. So if you're a little bit familiar with how Ethereum works, this is mostly like the state routes. So something that commits to the whole state of the layer 2 blockchain. So all that is posted on Ethereum, and the system is secure because there are other actors, verifiers. They download the transactions, the L2 transactions that you put on Ethereum. They download them, and then they re-execute them to check that the sequencer did the job correctly. And they rederive the output routes. Then they compare. If they get the same output route as the sequencer, everything's all right. No problem. If it's different, it probably means that the sequencer has a bug, or maybe it tried to cheat somehow. And in that case, you want to be able to challenge the result. Say, no, I verified this, it's not correct. And that's the fault-proof process that we're going to talk about. This process of challenging an incorrect result. So two things to note. These machines are meant to scale. So today you could actually run them yourself. But in the long run, you're going to need something much heavier, like a data center or something. And the other thing, which is written here, is that there's an additional security assumption compared to Ethereum, which is that you trust there's at least one honest verifier. So there's got to be one guy, maybe there's 10, 100, 1,000 verifiers, but it's got to be one that's honest, and you trust that. This is a very weak assumption, right? Like it's compared to a 50% assumption, just having someone that is honest is a pretty safe bet. And there are natural people that want to be running a verifier, right? If you're a bridge, it's in your own interest to run a verifier to make sure people are not exiting with funds that have been acquired through some kind of manipulation by the sequencer and that are going to reverse due to a fault proof. So you want to be running the verifier in that case. And we're already done. So this was the basic idea of what a rollup, an optimistic rollup, I should say, is. So how does the fault-proof work? And a big canon because our fault-proof system is called canon. Very subtle. So this is like a summary. The security depends on there being a verifier, as I said. And how this process happens is that first you do what's called a challenge game. It's a gameplay between two actors, and we call them the verifier and the defender. And really, to simplify, you can think of them as the verifier is a validator that disagrees with the sequencer, and defender is going to be the sequencer that defends, no, what I posted was right, and I believe in it. So the guarantee that is key to these rollups is that as long as the layer 1, so Ethereum, works correctly, as long as Ethereum is secure, then the challenger, if he's right, will be able to prove that indeed the sequencer misbehaved. So the key assumption is that the security of an Ethereum guarantees the security of the system by guaranteeing that incorrect statements can be challenged. And so this prevents like fraudulent funds to escape to L1. So this is just the same thing said in a different way. So you got layer 1, the verifier downloads the transaction batches, recomputes the output routes. It also gets, does this actually work? Yeah. It also gets the output route from L1. It compares them. If they're the same, you're very happy. I suck at drawing. And otherwise, you initiate this fault-proof challenge on L1. Okay, so how do you actually prove that you computed the correct result, but the sequencer computed an incorrect result? There's multiple ways to do it, and there's other ways that suck, as you can see. The first naive solution is to rerun the whole block on the EVM. This is not possible because there's a huge overhead into running an EVM interpreter on the EVM. Like, I put 100x, I don't actually know what it is, but it's huge. And simply, you're trying to run a block in a block with overhead, and so you don't have enough gas. Okay, what about something else? What about, Ethereum runs EVM anyway, so we could just take the L2 bytecode, put it on L1, right, and then run that. The problem is that there are contextual opcodes that need to be changed. So an example is this block number thing. Well, when you run it, you want it to return the L2 block number, not the L1 block number. Or when you read memory, you don't have the whole L2 memory posted on L1. So you need to somehow have a manager that can be fed the pieces of memory and get that to you. So this is quite complex. It still has a ton of overhead. You still need to feed all the data that the block is going to touch. And so it's not practical in practice. Okay. But what if instead of running a whole block, we run a single transaction? Maybe that's enough. Yeah, maybe. That's what Optimism tried to do, and it sucked. So there are a lot of subtle issues. There's still gas use issues. But like to highlight just one issue that's particularly nasty is that you need to take your contract, you need to deploy the bytecode on L1, and you need to patch the opcode, right, the contextual ones. The problem is that the patch contract is bigger than the original contract because you take your block number of code and you're going to replace it by a call to another L1 contract. And so that takes more opcodes. And that means that the size limit on the contract is going to be much smaller on L2 than on L1. And that's nasty, and you just don't want that. So the solution ultimately is to use a challenge game. The principle of challenge game is to figure out a single step in the execution that you disagree on. So if you disagree on the result of a 10,000 step execution, there must be one step that you disagree on. It might be the very first step, but it might be the step in the middle. And so what's a step? Well, it could be one EVM bytecode instruction, or it could be one assembler instruction. And I'll tell you more about that in a second. And so yeah, the challenge game is played between the validator and the defender. So our system is called Canon. The initial design and the proof concept was implemented by George Hott, who's famous for hacking the iPhone and the PlayStation. Yeah, he's a pretty fun dude. And we're developing it currently, including myself. And it's important to note that Canon is not the first system of its kind, and I'll mention just two alternatives, which are the Cartesy blockchain, which is fault-proof for like whole Linux programs, and of course Arbitrum. But it's the first fault-proof system that supports EVM equivalence, and personally I also think it's pretty slick in the sense that it sort of removes all the extraneous concerns and just focuses on the core of what you need to do. All right, so let's dig into the challenge game. So the challenge game performs what we call a bisection. If you're a programmer, you might recognize what it is. If you're not, don't panic, I'm going to explain. So the idea is that you have this execution trace. So if you run a program, you can create a trace that is a list of all the instructions that were executed. Then the question is, well, what program are you running? Well, you could be running an EVM program directly, so a transaction, and then your trace would be made of EVM outputs. Or you could be running the validation code, so the node code, Go Ethereum, for instance, directly. And then your trace is all the assembly execution executed when you're running Go Ethereum. This is what we do. So we do run a modified version of Go Ethereum that validates L2 blocks on L1. We call it minigeth. And basically what minigeth does is that it reads the inputs, the batches, it derives the layer 2 chain and performs the validation. So it's the minimal amount of stuff you need to verify that the output route is correct. And we compile it to MIPS. MIPS is an instruction set, and it's a simple instruction set. That's why we picked it, because it's easy to implement a MIPS interpreter on chain. And it's also easy to compile Go code. As the name implies, Go Ethereum is written in Go. It's easy to compile Go to MIPS. So this made it easy for us, and you know, we're lazy, and we like simple, easy stuff. So once you have this idea that you have this execution trace, you need to figure out which step in the trace is the step that we disagree on. And the way you do that is that you run the program offline, partially, until a certain step of the execution, and then you stop, and you supply a commitment to the memory, a hash, or if you know what that is, a Merkle root. So you start and you execute half of the validation program of minigeth. You stop at 50%. You take all your memory, convert it to a hash, you send that to a blockchain. The validator does this, the defender does this. On-chain, you verify the result. If it's the same, it means you at least agree on the first half of the execution, and so you will next submit a snapshot, a hash, at 75% of the execution. If you disagree, it means your disagreement is before 50%, and so you will submit the memory hash at 25%. And you keep doing this, shrinking the possible space of disagreement by half until you found a single step of disagreement. And this single step has the property that you agree on the memory before, so the hash of the memory, so basically you agree on the memory, before the step, and then after the step you disagree on the memory. So running the single step over the memory that you agree on will show that someone is right. You know, it will show who's right and who's wrong. And then once you have figured out the step, you actually need to execute it on chain, for which we use a on-chain MIPS interpreter, which is very simple, less than 4 lines of code. Two things are interesting is that at that stage, you only have a hash of the memory, but the hash doesn't give you the whole memory, and you still need to access some memory. Not much, because you're just running one assembler instruction, so you probably only need to access 1 or 2 memory locations. And you might also need, in a special case, to access the batches, and the batches already live on layer 1, so they're not in the memory, or at least you need a way to get them into the memory. So how do we do that? For accessing the memory, the hash of the memory, as I said, is a Merkle root. And I'm not going to explain Merkle root right now, but it suffices to say that if you have a Merkle root, it's possible to prove any byte of memory. So say the byte at location 100 in memory is 3. You can prove that using something called a Merkle proof. And so if your instruction is going to access the memory at location 100, you can make a proof of what that is, and you can supply that before executing the instruction. And then the other thing you might want to do is access the batch on L1. And for this, we use something truly magical called Premature Recall. And that's going to be explained in detail in the rest of this talk also. All right, so this is just the same thing I just rambled about, but illustrated. So this is your execution trace for challenger, for defender. These are the same size, but in practice, they could be different size. It doesn't matter. So each square here is an instruction in the trace. So you take this step, you take a memory snapshot, you compare them. Let's assume it's the same. Then you go to 75%. You compare the memory snapshot. In this case, it's different. You go in the middle, you compare, it's different, etc. You keep doing this until you've isolated a single instruction that's a single step of this agreement. That's the challenge game. And now, the Premature Recall. Oh, I'm sorry. All right. So the Premature Recall is a bit of a mind-bending idea, but the interface of it is very simple. It's just a function that, if you give it a hash, gives you the preimage of the hash. So this is normally impossible. It's impossible to invert a hash. And so, of course, say the Premature Recall is an on-chain contract, you will need to pre-supply the preimage. Otherwise, it's impossible to answer this query. But the program that uses the Premature Recall will assume that the oracle has access to the preimage that he's interested in. Some example of why it's useful to have this: if you have a block hash, the Premature Recall will give you the preimage of the hash, which is the block header. And particularly interesting is that every header has the hash of its predecessor block. So you can walk all the block headers if you just have this interface. Similarly, a Merkle trie. So Merkle trie, I guess I will explain it briefly. It's a tree data structure where every node can be represented by the hash of its children. And so if you have a node, so a hash, you can expand it through the Premature Recall to find all the children. These children are also hashes, and so using the Premature Recall, you can traverse the whole tree using just this interface, the Premature Recall. And basically, if you put all these things together, the result is that you can access any L1 data just based on this interface. You can walk back in the blockchain through the block headers as far as you like. And in every block header, you also have a Merkle root for the transactions, and you have a Merkle root for the state at this point in time. And so you can access any state at any point in the blockchain, and you can access any transaction that was made in the blockchain using this interface. Jesus. Okay, so this is the same idea illustrated. So say you start by running the block hash opcode to get the hash of the previous block. This will give you the block header. So it's this. It has a bunch of fields, but as the previous block hash, it has a transaction Merkle root that gives you all the transaction. Let's say we're going to zoom back to the previous blocks, block 41, through the preimage or the previous block hash. So, like, if you follow the green arrows here, these are applications of a Premature Recall. So we go here, we expand the previous block hash, then we expand the transaction hash. This gives us the root of a Merkle tree, and we can traverse that all the way down, and we can find whatever we're interested in. In this case, we want to look for transaction batches. These are stored in the call data of ordinary Ethereum transactions. Oh, I'm so sorry. All right, so how does this work in practice? Well, in miniGeth, so the miniGeth is this program that we run, that we get an execution trace from, and that we play the challenge game on. And so miniGeth re-implements the Go Ethereum database using the Premature Recall. And so that's how we were able to access like the state. And on top of that, and this is not in this slide, unfortunately, but there's a step before the validation of the block where we also read the transaction batches and derive the L2 blocks. And this also uses the Premature Recall. Actually, it uses it in the way that's like outlined here to find the transaction batches. So there are actually 3 implementations for Premature Recall. It's implemented on-chain. On-chain is very simple. You just pre-supply all the hashes and the preimages in advance. And because you only ever run one instruction on-chain, it means that you only need to supply a few preimages. To get these preimages, well, first, actually, I should say, you also execute it off-chain in MIPS. So you take miniGeth, compile it to MIPS, and then run that off-chain. Why do you need to do that? Well, because you need to find the memory hashes that we talked about in challenge game. And for this, it needs to be MIPS memory, because that's what will run on the chain. And these also use prefetched hashes. But in this case, you need the hashes for the whole block, the preimages for the whole block. And so how do you get these preimages? You get them by running the normal Go Ethereum, so compile to whatever your architecture is, probably x64. And in this case, we get the preimages using the JSON RPC methods. And the tool we use is get block by hash. So this is like straightforwardly, you give a hash, it gives you a block header. And this at ETH get proof. And this, you give it a storage slot, it gives you a Merkle proof of the block. And there are some very fun challenges in implementing that, because it's not exactly what you want, so you need to be very creative with it. But trust me, it works. All right, we're almost done. It was faster than I thought it would be. So in summary, optimistic rollups are secure as long as there's one honest validator. This is a security assumption. If the validator disagrees with sequencer, initiates a fault proof using Canon. And the validator and the sequencer play a challenge game where they exchange memory hashes until they find the single step of disagreement. Once the step is found, it is executed on-chain, supplying preimages of the memory, which can be proved against the Merkle root of the memory. And and batches can be read from L1 using the Premature Recall. And where are we with this? So George delivered a prototype to us, which allows you to challenge L1 blocks on L1. This is not super useful because L1 blocks are correct by definition. But it showed at least that the idea could work. We've been playing with it a little bit. And so what we have now is almost just a very simple port of this to L2, so proving that our changes to geth or L2 don't break anything. So we can challenge L2 blocks on L2. And what is next is to actually do the real thing, which is to challenge the L2 blocks on L1. And so what's necessary for going from here to there is that it needs to add this step of L2 chain derivation, which basically reads the batches on L1 and derives the L2 blocks from the batches. And if you're interested in that, my colleague Josh will have a talk, I think later today, about that. So about Bedrock, which is the next version of the system. And I think he will go into detail of chain derivation from batches. And if you really want the detail, tomorrow we have a workshop. Come talk to me, I'll give you an invite. And we'll cover technical details of both Bedrock and Canon tomorrow. And yeah, so last detail. This might seem like a lot of work, but actually this is work we already did, because our rollup node, so the thing that runs the blockchain, already needs to read the batches. It already needs to derive blocks, otherwise there would be no blockchain. And so what's fun is because minigeth is a Go program, we can just use Go modules and import the logic that we already wrote and reuse that directly into minigeth and then compile it to MIPS. So that's pretty neat. It requires some sacrifice, like when we compile it in MIPS, it's like fully single-threaded, so you can use channels and things like that. But otherwise, if you think about it in advance and write the module in the first place to be compatible with Canon, so just don't do multi-threading basically, then it works pretty neatly. So we don't expect this to be a huge undertaking. And we're done. And yeah, there's plenty of time for a few questions. Okay.
Hello.
Yeah.
And nice presentation.
Thank you.
Just wanted to ask you mentioned at some point that for most of the opcodes, you did need just one memory zone, so one memory access or something like that.
Yeah, or two or three, but
two
not
or three.
a lot.
Yeah, but there are some special opcodes like create or ext, the one that you get the hash of a code, or even deploying a transaction itself. You need to prove that you deployed that transaction. That this requires a lot of access. to memory. How you handle that? You partition that in many select subparts, or how you're handling that?
So that's correct. The key here is that we're not actually using EVM opcode instructions. We're doing it on MIPS instructions. And so actually the MIPS code in Go Ethereum runs an EVM interpreter, and that uses the MIPS instructions, and the MIPS instructions in themselves, they don't have these cases where they access a ton of memory. So in reality, if you deploy a contract, you only ever challenge a tiny piece of the logic for implementing that.
So you implement the full opcodes on Ethereum in this MIPS language somehow?
Yeah, but the key is that we don't implement anything because we just take Go Ethereum, which we modify. We're very careful about making a really minimal modification so we can always keep up with upstream. Like we have like literally one commit on top of upstream Geth.
You recompile Geth?
Yeah.
Okay.
Totally, to MIPS directly.
That's
yeah.
interesting.
Like I said, we're super lazy. Yeah. Do you want the microphone maybe?
Yeah, question regarding the threat model in the challenge game. So basically, to find this step which differentiates between the validator and the sequencer, both of them need to compute the hash of the memory, right? And is there some trust that they will compute this hash memory correctly for every step in order to go to this step that it differs? Because I was thinking like what happens like for the 50%, both of them compute the hash correctly, but then every other hash differentiates. So basically this will lead to the step 50% plus 1, but the real difference would be, let's say, at 95% or something like this.
So the assumption, the base assumption is one of them is incorrect, right? Like one of them is lying, so it is already baked in. And so in your scenario, if they agree at 50%, and then they always disagree, then they will end up saying that the last step that they agree on is actually the 50% step, and that's the one that you will run on-chain. And then, because they both committed to a hash for after that step that is different, like we verified that, because otherwise you would have taken another step, right? Because they both committed to it, you can just run it on-chain, and then you'll see who is right by getting the result directly on-chain, guaranteed by Ethereum doing the execution correctly.
Okay.
There's someone there has that question.
So I assume that this challenge game overall requires some tens or hundreds of transactions. And then how do you defend from possible denial of service attacks based on multiple simultaneous challenge games?
It does not require, how much you say? Yeah, it requires a few tens of transactions. Because you take the size of the trace, and because you cut the space in half each time, it's a logarithm. So if you had like 4 billion instructions executed, it would take you 30 steps. You know, and it grows fast, right? Like if you want 16 million, it's just like, you just add 3 transactions.
Yeah, okay, I get it. But what would happen if hundreds of different challengers will try to challenge and start this game at the same time?
Then it's DOS on Ethereum, not on us. But there is something interesting there, which is yeah, basically making sure that all challenges that have been initiated are able to complete. And we haven't decided what we're going to do yet. We're looking at the options. I think it's possible we end up with a design that's very similar to what Arbitrum is doing, which is that you would basically wait for every challenge to complete, and there's like some kind of expiration window. So you do have to answer within a certain time bound, but if the parties are adversarial, you could it could take a while, but every challenge eventually times out or completes. Yeah, we really need to look into that, like what are the exact assumptions, how big the time bound needs to be, like, and this comes down to how costly it is to censor someone that would be honest, would want to do the challenge. How much does it cost to censor them on the long term? Because that's how you differentiate like a censorship from someone that just playing the clock and just trying to DOS the chain by waiting. Anybody else? Dumb questions are accepted, by the way. There's no dumb question.
Can you talk a bit about the security assumptions of the pre-image oracle and like anything around where that could fail and yeah?
Okay, so the simple answer is that it's secure because you supply the pre-image and then you hash it and then you just get a hash. And so that's verified on-chain, you just do hashing on-chain. The complex answer is that there is one pitfall to it, which is that most of the cases in Go Ethereum when you won't want to use the pre-image oracle, the pre-image is pretty small, right? It's a block hash, block header, sorry, or something like that. There's one case where the pre-image could be huge, and that's the receipts. Because the receipts, they encode all the events that have been emitted during the execution of a transaction. And if someone wanted to DOS you, they could just emit a huge amount of zeros. They could use like a whole, like the worst possible case. They just take the whole L1 block worth of gas. I didn't give the context for that. Okay, quick context is that you can, if you want to bridge from L1 to L2, you can do what's called a deposit, and that's an L1 transaction that will bridge over to L2, basically. And to read them, we read the events that they emit, because there's a deposit event. And so to derive the L2 chain, we need to read these events from the layer 1 blockchain. And so we need to invert the hash of the receipts. And this pre-image, if someone was maximally malicious, they would take up a whole block, a whole L1 block of gas, and just emit events in a single transaction. And that could be like hundreds or even a gigabyte or so. And yeah, you can't post a gigabyte of data on Ethereum. That's a pretty big DOS. So we're looking at solutions there. What I think we'll end up doing, my best guess currently, is that we'll do a very simple zero knowledge proof. So that, because we're running MIPS, MIPS never access a bunch of memory together. It only needs 1 byte or 1 word in that receipt. And so you can do a zero knowledge proof to prove just 1 byte of the receipts. So, and you can probably do it with something very simple like Circum that's like available off the shelf. You don't need to invent a whole new kind of ZK. So I think we'll do that. Nobody else? Okay, quick feedback. Was the talk like easy to understand? How's the difficulty level? Who was completely lost? Don't be shy. I've been to plenty of talks where I was completely lost. Who got half of it? All right. Who got mostly everything? You know, maybe not everything, but like, yeah, a big chunk of it. All right. Either I'm great or you're all very nice. So if you have any questions left, don't hesitate to come find me afterwards. I'll hang around, and I hope we can chat. And like I said, tomorrow we have this workshop, so hope to see you there. You need an invite though, so hit me up. And I'm NorSwap everywhere, basically. Twitter, Telegram. Add me if you have a question, if you don't find me. Thank you very much.